Welcome to Badger Talks Quick Picks, which brings exciting happenings, resources, and talent from your UW flagship campus to the people of Wisconsin and beyond, demonstrating the power of the Wisconsin idea, one connection at a time.
Hi, welcome to this Badger Talk. My name is Jennifer Choy. I'm a faculty with the Electrical, Computer, and Engineering Department at the University of Wisconsin-Madison. Today, I'm going to talk about how atoms can act as tiny metronomes that let us keep superb time, navigate anywhere, and sense very small fields. The atoms that I'm going to talk about today are the same ones that make up everything, but we prepare them in special ways. We isolate individual elements or isotopes and measure single electron transitions. Atoms of a specific element glow into characteristic set of colors, and these form an atomic fingerprint. The reason for this is due to quantum mechanics. Electrons in atoms like to sit at specific energy levels, and they emit and absorb specific colors of light. We actually have seen this type of atomic fingerprinting in the sky. The colors of auroras are actually coming from atomic emissions. And in the picture here, we see these beautiful green and red colors that are coming from excited oxygen and nitrogen in the high atmosphere. And when these atoms get excited and they relax, they emit these specific colors. So we can actually make atoms glow in our lab and sometimes even at home. All we need are ways to basically isolate the atoms, and we can do that in a vacuum vessel like this, and we need to put in a lot of energy. So I would like to show today how we can do that. What I have here is a Tesla coil. It produces high voltage. And I'm going to put next to it atoms that are confined in glass tubes that are shown here. And specifically, I have in these glass tubes neon in one tube and helium in the other. As I approach the tubes close to the Tesla coil, we basically see glowing in these tubes. What's actually happening is that the high voltage is kicking electrons away from the atoms, and when they relax, they're emitting in characteristic colors, and we see different colors from different atoms. So now I'm going to talk about how we can turn these atomic fingerprints into oscillators. So as mentioned, atoms are emitting in specific frequencies. And if you are hitting these specific frequencies, that will actually enable the atoms to ring, much like a tuning fork. And what is actually happening during this ringing is oscillations in optical and microwave domain. And this corresponds to basically the electrons oscillating. And this animation that I'm showing here is illustrating that. So now we have an electron in the atom that is oscillating, and is oscillating at some frequency that's specific to that atom. If we have a way to count these oscillations, we have basically generated a clock. What makes this clock so special is that the frequency at which these atoms oscillates are universal, meaning that an atom that is in Wisconsin is going to oscillate with the same frequency as an atom, that same type of atom in space. And this is very different from, let's say, our mechanical watches, where we have to compare mechanical watches with respect to each other and tune them, and actually just tune them periodically. And that's what makes atoms such a great clock. So the different frequencies, and we can think of these frequencies as tick marks, much like, little tick marks in a ruler. These atoms oscillate at frequencies that span basically from billions of cycles per second, such as the case of a cesium clock, to hundreds of trillions of cycles in a second, such as the case for a strontium clock. And if we were to compare these frequencies to the oscillation frequencies of, let's say, mechanical or crystal oscillators, which are used in our watches, right, or in older types of clocks, we see that the frequency at which atoms oscillate is many, many times faster than the frequency that these other clocks oscillate. And that actually means that you are able to tell time with a much finer precision. And currently, how we define a second is actually with the oscillation frequency of cesium atoms, which is ticking at 9 billion times in a second. And the atomic frequency is actually sensitive to very, very small changes in electromagnetic fields, and also even in acceleration. And so if we're able to measure these very, very small changes in the atomic frequency, we can actually also sense the environment. So what are atomic clocks and sensors good for? First, cell towers and financial centers and data centers basically rely on very precise time steps that have to be aligned relative to each other. So if we use clocks that are referenced to an atomic time, then basically we have distributed systems that are going to be stable relative to each other, and information can be secure. Today, we currently use GPS to get us to where we need to be. Turns out atomic clocks are on basically all of the GPS satellites. And when our phone triangulates signals, it's actually doing so relying on an atomic timestamp. If that clock is even a little bit off, then we'll lose our position within a matter of seconds. And we are also developing atomic clocks and sensors to basically work in environments where you have no GPS, where GPS is obstructed or spoofed. And this can happen when you're underwater or in a tunnel. And therefore, if we're able to use atomic sensors in these scenarios, we can basically navigate anywhere and anytime. So what happens if we want to make the atomic sensor small? So far, I've showed you an example where we still need to put the atoms in a glass tube like this. Can we make it even smaller? Turns out you can actually create artificial atoms using semiconductors. And these are the same type of semiconductors that you would use in your computer systems. And an example that I'm going to show you today is color centers in diamond. And it's shown here on this left image with these beautiful colors that are coming in from diamond gemstones. And we can actually also make diamonds in a lab. The middle pictures here are showing you basically lab-grown diamonds. And what happens is we are creating small amounts of defects in these type of crystals, and each defect is corresponding to it a type of atom, an artificial atom, so it will in the solids. And here I'm going to show you an example of that. I have here a diamond sample. It's lab grown, and by itself doesn't look like it has any remarkable colors. And before we light it up, I want to show this diamond lattice, where each of these black balls is corresponding to a carbon atom. And each of these atoms you can think of as being 1,000,000 times smaller than the width of your hair. In the middle of this crystal, we have this defect. And again, this defect basically has the same size of an atom, and is represented here with this blue ball actually representing nitrogen. And this defect basically causes the electron around this part of the crystal to basically only occupy energies that are very specific, much like an atom would. So then when we give it energy, it will get excited, and when it relaxes, it will emit in specific colors, and in this case, a red color. So if I were to shine this diamond with a flashlight, in this case a UV light, we'll see it glow. And indeed it does, it's giving a reddish fluorescence. And what's so special about this type of artificial atoms is that it can be made very small. So small that you can actually put it inside living cells. And on this right image here, I'm showing basically pictures of tiny diamonds that you're putting inside living cells, that when you're measuring the red fluorescence that I was just discussing, in addition to applying microwaves, you can actually sense tiny magnetic fields so that these diamonds are acting as small magnetometers, which you can think of as a compass, and in some cases, a thermometer too. So to wrap up, hopefully I have shown you that we can use atoms and artificial atoms as tiny metronomes that can help us keep time, navigate anywhere, and sense invisible fields. Thank you very much, and go Badgers!